Esses talvez superam bem o 10ª temporada aí. Cada exemplo é serviço, 5 a 6, the rest of the pior.
Is part and parcel connected with our ability to scale up steam engines, the production of machines, the Industrial Revolution, in which, we start at around 1800s, and it's still continuing today at some level. Whereas later on in the 20th century, we added to that also what is known as the silicon age, the ability to manipulate semiconductors, because again, we became somewhat clever and learned quantum mechanics. And that allowed us to make semiconductors, which ushered in the electronics age. And that continues to this day, where we can now store information in electrons, in quantum computers and stuff like that. So suffice it to say, materials are intimately connected to the socioeconomic evolution of humanity. So we tend to consider materials as an enabling technology: semiconductors, electronics, polymers, plastics, membranes, biology applications, metal alloys, anything infrastructure almost will evolve on the ability to make metal alloys. Ceramics, thermal insulation, biomaterials, very important for drug delivery, prosthetics, etc. So there's something called the materials triangle that scientists and engineers are sort of, feverishly trying to always argue when they ask for grant money to do research to innovate materials. One is saying, I want certain properties to come out of material, you name them. We know that by and large, it all is predicated on their internal microstructure. And the microstructure is made, usually spontaneously, but we'd like to design it through the process. So this triangle, every material scientist and engineer can argue is somewhere on that triangle in the research they do. I'm more here with my group. So here's an example of an engine block, and it's zoomed in at different length scales. And apologize, my pointer, Valentina, do you have that pointer after all? Because my pointer battery, I guess, must be weak. This engine block here, what it's showing is different zoom-ins of
You seem to be working though.
yeah, on and off, so it's on the fritz. Yeah, oh, good. So here's the engine block, and here are different zoom-ins. So you take a piece here, zoom it in, take a piece there, zoom it in, take a piece there, zoom it in, take a piece there, zoom it in. And we're going down, down, down in scale. The picture here shows what the length scale of the picture is: millimeters, meter, micrometers, nanometers, single atoms. And underneath are listed all the well-known properties that that engine block will endure, will have, and how these properties are essentially dominated by the structure at that scale. So for example, the yield strength, the strength before which the engine will just bend, it just won't look like it does anymore. Cylinders can't pump on a deformed engine. Is taken care of by this labyrinthian structure called dendritic structure. The stiffness of the metal is predicated by the bonding of its atoms. So pretty much most of the properties you'll see live on this so-called mesoscale, larger than atoms, but smaller than the size of the object itself. And so entire industries, especially like automotive and transportation, have been built on understanding how to design or assemble materials that come up in patterns like this when you look at them under the microscope, such that you heat them, beat them, torture them, twist them, whatever, on a larger scale, they act like the words say. Here's another interesting one from some years back in Scientific American. If you look at suspension bridges, the size of suspension bridges is part and parcel connected to the ability to create cables called eutectic cables, one of the materials used, that become stronger and stronger. And so there's a clear link between our ability to communicate via bridge and our ability to actually make stronger metals. My favorite, aerospace. Aerospace is one of the most awesome collections of electronics, material science, hydrodynamics, material science again, put together by the human race. At its core is structure. And after you take care of the programming of, make the plane go this way or that way, depending on the winds, that's kind of straightforward. The biggest limitation in aerospace has always been materials, especially aerospace that needs to go faster and higher. Here's a picture, no point, I'm not going to go into the details of that, but here's some very specialized microstructure specifically created for aerospace metals that tell the engineer looking at this, what kind of strength these wing panels will have. It's a very delicate balance. Your wing, you want it to be strong, but you don't want it to bend plastically. Imagine what happens if the wing breaks. Two ways to break. One, it can fly right off. That's bad. But way before it does that, it might just sort of bend and not come back to its taut, rigid location. What happens then? You still die. Right? The slightest permanent deformation in a wing could lead to catastrophe. So there's a fine balance between designing alloys that are both hard, stiff, can bend a little so they don't fracture, but not bend enough that they stay permanently fractured. It's a science, it's an art all put together. And the microstructure is quintessentially the only thing that matters. This wing, by the way, on the new aircraft will bend. The 777X will allow this wing to break and sort of fold over so it can fit in airports, but then when it flies, it'll open up so it can get more aerodynamics, less drag, because there's less vortices at the end. Okay, so let's go into the talk problem. The role of materials in disasters. So disasters in society are often linked to failures of materials. And failures typically linked to two sources. One is faulty design. So the example, which I won't talk about because that's kind of straightforward, is the Boeing 737 MAX that you've all heard about in the media. I've even had the displeasure of flying one recently. I had a few drinks before I flew because, who knows? We've cut corners so many times and failed at it. At this point, who knows who to trust who? But this one was simply a matter of Boeing didn't want to redesign the plane. They had a new engine, so it was just simpler to put it on the old frame and just move the engine forward a bit. And then they told the airlines, hey, you don't have to retrain your pilots, much more efficient plane, go for it. 2 planes crashed within 2 years. Kill everyone on board. What was happening is the repositioning of the engines on the wings was causing the plane to fight the autopilot, and both times it would crash. Apparently they fixed that now. So that's faulty design. Another one is the physical properties of materials. That's what we'll focus on here. Basically, negligence in terms of what materials you're using and knowing what properties you want. Inappropriate selection of what materials are needed for a specific application. And poor knowledge of the physics of how materials work. And that's in red because most of our three talks, or three examples I'm going to illustrate for the rest of the talk are based on the red and a little on the first one. Okay, so let's see what we're going to talk about here. There's lots to talk about. If you're a Mayday fanatic, there's a show called Mayday that talks about all the airplane disasters. They can go on for days. So I picked three because they're close to my heart historically. One is the Space Shuttle Challenger in 1986. I remember I was in class when that Challenger blew up, and it felt like everything just stopped. It was a little like, not as extreme, but it was a little like 9/11, because the pride and joy of NASA, the space program, finally was shown to be vulnerable. And I remember all classes just stopped that day, and we were all trying to figure out, watch the news, just like we were for those who were alive. I think all of you were alive 9/11, but probably babies. Another one that's less known in the public eye is the BOAC, or British Overseas Airways, Comet airplane crashes of the 1950s. That was truly just poor understanding of materials. And last but not least, a talk like this could have happened if we didn't talk about the Titanic. Even though it's over 100 years ago that the Titanic sunk, it still continues to surprise to today. As a matter of fact, the root cause of what caused it to go down was not really known until the 90s, figured out till the 90s. People had it wrong for the largest part of the 100 years since it crashed. So let's address each one of these. And what makes these specific disasters interesting, again, is that they all sort of hinge on not understanding properly the physics of how materials and their structure, properties and structure relate. And like I said, a little bit of engineering negligence, especially on our first example. Absolutely. Well, so 1986, when some of the younger people in this crowd, I know were not alive, I used to give this talk as part of an ethics talk at McMaster. Engineers have to take courses in engineering ethics, which includes diagnosing what went wrong and chain of responsibility and which head role, etc. And I remember for the longest time I used to say, you all remember, and so the professor who taught the course said, well, the guys actually kind of stop saying, do you all remember? These people weren't born. So now I've learned my lesson. For those that were alive in '86, great. A lot of you weren't. The day that the Space Shuttle Challenger took off on that day was 0 degrees Celsius outside. And we'll see why that's important in a bit. What happened? Here is a shot of the Space Shuttle taking off. The Space Shuttle was essentially a rocket that was put on the back of a big bomb full of hydrogen, and it was just launched into space. And right here, you can see something you couldn't see if you looked at other successful Challenger or Space Shuttle flights. A telltale sign that something was about to go wrong. This was going wrong. The whole thing blew up. Like literally, if you see the TV reruns of this, the time between here and the blow up, you have to slow down the frames to catch it. So what happened? And of course, everyone perished, unfortunately, because the flame that engulfed the aircraft that came out of here just engulfed everything and just blew it up. So what happened? So it turns out, so I'll give you the answer and then we'll go through the why. So the space shuttle has so-called O-ring polymer. So this thing here, that's the orbiter. That's the thing where the astronauts sit in white. This big tank behind it in orange, filled with helium, has 2 rockets on the side, out of which hydrogen is ignited and flames come out. but it's a big long rocket, but it's not built as one continuous object. It's built in stages. And the stages lock. And the lock is sealed with something called an O-ring. It's a rubber material that's supposed to, when heated, expand to seal the joints between the interlocking tubes. So think of a big tube broken in 3 pieces, and the pieces are fastened together and sealed between them with a thing that will expand when heated. So as hot gases go through the tube, they don't come out the joints because they're sealed with an O-ring. So this O-ring is a polymer and it acts as a seal. The gases that go through the tube, as I just mentioned, heat up and they expand. So there's the polymer. And the gases are sealed in by the O-rings. When the shuttle blew up, President Reagan created a presidential commission called the Rogers Commission, and he put them to the task of figuring out what happened. And what was determined by largely one member of that committee, who happens to be a physicist, and who happens to be the one person on that committee who didn't have any skin in the game. And he had a Nobel Prize, so he actually didn't care. Whereas, as it turned out, many of the other people were willingly or unwillingly not really seeing the truth in front of them for a variety of interests and reasons. And so what was determined is that on the day of the flight, this O-ring, the thing that seals, cracked. It's supposed to heat up and expand, but this thing cracks. And so the crack allowed a little fissure through which hot, very hot, high pressure gases move through. That's this thing right there, leading to that. Okay, so let's see how it happened. So that's what happened. The O-ring cracked, gases leaked out, kaboom. Why? So it turns out every material, when it's heated, expands. And when it's cooled, contracts. And this is called thermal expansion. So here's a little cartoon of material that's cold. That's why it's blue. I colored it blue. And then it heats up. Then it looks red. I colored it red. And you see when it heats up, it gets a little bigger at the final temperature, T final. It's a little hotter, then it opens up. And engineers have a formula to sort of prescribe this stretch. The final length minus the initial over the initial is related to the final temperature minus the initial. So think of this as how much has the temperature changed? So say it's heated up. That's the T final minus T initial. And there's a proportionality constant, the thermal expansion coefficient, that tells you by how much is it going to stretch. Okay? So for every Kelvin of change in temperature, the material expands to the tune of alpha. Why does this happen? To get up close and personal in the material under a microscope. So suppose you're a little Maxwell Beaman and you can actually go in the material while it's expanding and watch what its atoms are doing on average. What you're going to find is at the low temperatures, the atoms have a certain space in between them because they're nice and orderly, because they're solid. It's a solid you're thinking about here, not a liquid. And then at the higher temperatures, the space between the atoms moves. Put that together over gazillions and gazillion atoms, the whole material in the real world expands. And so here's a look at how things expand depending on what material they are. So the larger the number, the more things can expand. The smaller the number on the table, the less things expand when heated or cooled. Because I say expand, but you should read expand or contract depending on which way the temperature goes. So you see that the polymer stuff tends to expand more. That's why they were using polymer O-rings in the connectors between the tubes through which hot gases were going to flow to power the orbiter so it can take off. Makes sense that we would use polymers. Whereas if you go down to ceramics and glass, they have very little thermal expansion. And the glass is very brittle. You just expand their big little crack. So you don't use that for these applications. So what gives? These polymers had a lot of thermal expansion. They should have survived the expansion. They should have done their thing. But notice here it says at room temperature. What this graph doesn't tell you is that certain materials change by how much they can expand depending on how warm or how cold they are. And so here's a graphic that if you're into stress strain mechanics, great. If not, don't worry about it. But for those who have seen something of stress strain mechanics before, on the y-axis is the stress. How much stress can something take? On the x-axis is how much can I pull it? So think of a spring. If I pull, strain it, it'll build up its stress. So a spring is kind of linear. The more I pull, the more stress I feel. So that would be something like this. This says that as I pull, I feel some force and it starts to just slide out. Think of your polyethylene garbage bag. You pull it, it's stiff for the first part of the pull, then it starts to just come apart like glue. So that would be this. And most polymers follow this prescription because you want them to do that. You want them as a stretch to sort of flow, not crack. However, it turns out that these curves are all for the same material. All that's changed is how cold the material is. The material is really warm here, really cold there, 4 degrees versus 50. So this is an unfortunate trick that polymers also do. They stay gooey and flowy and expandable at warm temperatures, but they get brittle and don't like to stretch and flow at cold temperatures. So at 4 degrees, this material, whatever it happens to be, it's PMMA, is very stiff and brittle. At more than 40 degrees, it's very flexible and high ductility. So the O-ring polymer, the engineers who designed it, had a certain temperature range in mind that the orbiter would operate at, and they assumed that it would always be somewhere in the range of temperatures, somewhere between, less than 40 degrees, but, Florida could get around 30 to 40 degrees on a hot day. So they assumed it would be somewhere in the range where it can be ductile enough to expand and not crack. The thing is, things that tend to be stiffer crack easily. Things that tend to float don't. So what it turns out was the root cause of this disaster was negligence, because it turns out that Morton Thiokol, the company that produced the O-rings that went into these solid rocket booster components, knew, and they had urged the night before the launch NASA to not launch because they knew the next day the forecast had been for cold temperatures, colder than, say, where the whole O-ring polymer would act this way. More like maybe where it would act this way, where it would just be stiff until a certain point, and then notice this curve doesn't continue, it would just stretch. And the engineer's name voiced serious concerns. And at first, he was essentially, the commission later found out, threatened by his bosses to not speak up. And he was overruled, and the launch proceeded, and the rest is history. Now, the interesting thing is the commission who figured out what I'm now telling you took a while, but the person who actually figured it was a fellow by the name of Richard Feynman, who somehow found himself on this committee. And in his book, surely you're joking, Mr. Feynman, I think it is, because it's been over 30 years or plus maybe 40 that I've read those books. He actually took an O-ring polymer that was at the temperature that the orbiter had been sitting at on the tarmac that day in Florida, and took a glass of water that was cool and put it in and showed that in the reverse way, but it's the same effect as the thing heats, cools down, it actually cracked. So he did a little demo in front of the committee's eyes and made it unequivocal that, stop looking into the skies and to the cracks in the walls and where this is the physics of what happened. And it kind of broke the case wide open. I'm sure they did more follow-up then, but it took him, and again, the main thing is he had no skin in the game, so he was able to tell the truth without fearing repercussions. So that was very interesting, not just in the disaster, but also the follow-up was almost as dramatic, almost a big soap opera as the actual event itself, I remember back then. Okay, story 2. You like the stories? Good, so we continue? All right. At this point in my class, I would do the wave, so everyone wakes up. You're all look.
When Vasudev was overruled, was it one person who overruled or a group of people?
The engineer, his managers. And the reason was because there had been a series of delays in launching at NASA, and the public image of NASA, I mean, they also took a big hit in this. It wasn't It wasn't just the company, it was they had to deliver the product and NASA didn't want any more delays. So it flows downhill. Okay, so this is the Comet airplane. BOAC is the industry. It doesn't exist anymore. It's called British Overseas Aerospace Corporation. And this was a plane they had made circa 1950s. Here's one flying. Here's one not flying. It was picked up from the ocean floor 2 years later. This is what happens when this sort of destructively explodes in the air, falls into the ocean, and to this day, most aircraft, after they have fatal crashes, there's an attempt by the NTSB to put them back together by jigsaw puzzles so they can identify what's going on. That's kind of standard procedure, even if it takes years. So what happened? So the Comet vanished from the sky. So in 1954, after 18 months of service, 2 aircraft successively disappeared 3 months of each other. So they were literally flying, everything was going well, then they just vanished. Both sort of transcripts show nothing leading up to the accident, nothing said by the pilots, nothing. It's almost like, they just zap out of existence. An investigation was launched by the Royal Aircraft Establishment, and they concluded, probably after picking up the pieces from the ocean floor, that both fuselages suffered catastrophic fatigue failures. Fatigue is when a metal has been used so often. So it happens one of 2 ways. The metal basically is used so often that there's cracks inside, and if you don't repair the cracks or create new panels without cracks, those cracks open until they become long enough that one more push and the whole thing destructively cracks open, taking an entire aircraft down. The interesting thing here, and this was truly about understanding, no negligence. The interesting thing here is that the engineers were completely scratching their heads on this one because the metal and the amount they had used, they claimed, were both enough that the flight forces should not have brought any of these planes down, should not have caused a crack in an otherwise relatively new piece of metal, because these were pretty new planes. So the cause remained a mystery for quite some time. Here's a letter. The last time I gave this talk in 2016, there was an elderly lady in the audience who after the talk came up to me and said, I had my fiance in New York City and I sent him a letter on one of these aircraft that crashed into the bottom of the ocean. So when they reconstructed the aircraft, they also got some of the cargo, including the mailbags. And they send her back the letter to her fiance. And she was kind enough to share it with me. So here it is, a real live letter. And she was from Montreal, actually. Living in New York at the time. Sorry, in England. The fiance was in New York with plane of second. So I thought that was kind of an interesting echo from the ocean floor to just see this. It's mesmerizing. You can't imagine where it is, what it's been. So how did this happen? So again, we bring up the plane, we reconstruct it like so, and they start looking. They start looking for telltale signs, the materials engineers knowing in their head the relationship between properties, performance, etc. And there's something, this is a portion of the fuselage showing a window, and you see a gash here. And there's something about this picture that immediately shows a potential culprit that may have brought this plane down. And I'll have you, a little anecdotally, I'm not going to talk about this, the exact same cause or very similar cause to what caused these planes to crashes also was the reason Aristotle Onassis, if anyone knows Aristotle Onassis, he was a Greek tycoon in the 50s, he became extremely wealthy, exploiting, without understanding, what brought this plane down. So that's a topic for another day. This time on ships. Okay. So there, just to point to your attention, what is the root cause of what causes planes to crash? The windows on these planes were built like squares, roughly. Notice today when you want a plane, you notice they're ovals. And you can't really look left and right. That's not because they're trying to be annoying. There's a reason. They want to minimize how much hole out of the fuselage rotating. Back then, they were square link. And notice the gash is somehow linked to that corner. So let's look a little bit at stress mechanics, very basic stuff, and let's see if I can convince you of what the root cause is without us having to go into too much detail. So here's a piece of metal. It's a piece of panel of a metal, and I put a hole in it. And the hole has a length 2A. A is a number, it's just a length. And I stress it. So I pull it apart, and there's a hole in it. It turns out near the corners of that hole, a huge stress is going to build up. How much of a stress will build up? So let me zoom into this crack tip. That's what's shown here. This, imagine, is a zoom in of a little bit of that crack tip in my cartoon here. And rho t means the radius of curvature, how curvy, how sharp. So think rho small, sharp tip. Rho big, blunt tip. And here I plot the distance away from that crack tip. So I walk away from it, and here I'm plotting the blue line, how much stress it's feeling. So I take a plate with a hole, I stress it. That's what sigma 0 is. I look near the crack, different distances away from it, and I ask, how much is the stress going to be? Very far away, it's just going to become the stress I'm applying on the metal. Very close to the crack tip, the stress can dramatically increase. So, takeaway, if I have a panel of metal, anything, let's say metal, because that's what they were made of, and there's a little crack in it, as I pull, who's pulling? The air pressure, because all planes are pressurized. Away from the crack tip, the stress is just whatever the nominal stress is that the engineers accounted for. Near the crack tip that the engineers didn't account for, the stress from the pull of the fuselage being pressured, the stress can jump up dramatically. Many times, almost tenfold, depending on the sharpness of the tip. So we call this the stress concentration factor. So all you need to know to take away from this is that the stress concentration factor is a ratio. Length on the top, sharpness on the bottom. So the longer it is, there's more stress at the tip, or it could be short but very sharp, there's still stress at the tip. Let me give you an example. You can try this at home. Take a cue card and take a hole puncher with a pair of scissors and punch in 2 cracks into your cue card. So pick an ordinary cue card and cut a little slit crack like this with your scissors. And then at the same height with your hole puncher, crack in a crack that's more blunt. See, crack, crack, very sharp crack. So the road here is tiny. Same length of crack, but the row curvature is much larger. And then take your hands here and just pull out the cue card. Which crack do you think will crack the cue card first? The one on the left or the one on the right? Who says the one on the left? Who says the one on the right? That. The one on the left will go first because it's sharper. Its stress concentration factor, all other things being equal, is higher because it's a sharper tip. Repeat the same experiment with slightly different conditions. Now take a hole puncher in both cases and make the crack have the same bluntness or radius, but make one crack longer and a crack shorter. Again, pull the cue card. How many people say the one on the left will crack first? How many people think it's the one on the right? Exactly. So the stress concentration factor is larger for the longer crack and larger for the sharper crack. So the two play in tandem with each other. So a long sharp crack is horrible. It really amplifies stresses much more than the nominal stress. So you might be thinking, okay, I'm applying so much stress, no problem. But there might be a crack nearby where at that point the stress has gone very high. How high is very high? So it can become so large for any applied stress that it's not possible to sustain the stress. In 1921, Arnold Griffith developed a criterion for what stresses will crack, or when a crack of a certain length and a certain sharpness will crack. For what applied load will that crack actually open up? Called the Griffith's criterion. Ironically enough, He developed the criterion in 1921, and yet the BOAC engineers have not read the papers most likely in 1950s. And this is not because they were negligent, this is typical. We do science today, which ends up finding itself into engineering applications in 10, 15, 20, 30 years from now. Sometimes quicker, sometimes longer, depending on the climate, the politicians, the funding. So it's not like anyone did anything wrong. Chances are this Griffiths criterion that we call today was just lurking in books and scientific journals, but engineers just were not aware of it. And what it says is, for again, a little bit technical, that the cracks will grow when the elastic stress energy stored is greater than that needed to cause fracture surface. So let me give you a little cartoon argument of how this works. Here's our material, like this, and a little crack has appeared. I'm going down to the atomic level, and in my cartoon, atoms will be connected by springs. Over here, this little two lips are really the beginnings of a crack opening. And I'm pulling. You see these stress arrows here? They're pulling down and pulling up, and a little crack is opening, ripping the bonds. And so I asked the question, how much energy does it take to create these free surfaces? It turns out free surfaces are not a good thing in nature. They cost energy. They always cost energy. The surface between the table and the air costs energy. Our skin in the air costs energy. It's what we call a positive energy surface. You never relieve energy by creating a surface. You create it. So there's some energy associated with these free surfaces. To the tune of how long the crack is, times a certain number, that's a property of the material. At the same time, the fact that you're pushing on this material that hasn't yet quite cracked open is creating a stress throughout the material, an elastic stress. And that goes like the length squared. The details of these are not important. It's just suffice it to say, if I stretch a material with a crack, there's a crack having two surfaces about to open. They're not like by nature. There is a material holding onto itself elastically as you're stretching it. The two are competing with each other. It turns out that if I plot the total energy, and another little factoid is that most systems in the world, they like to live in a place where they lower their total energy as much as possible. The materials don't like living with lots of energy. They like to go to a place where the total energy, simplifying a bit, is lowest. So it turns out if I look at the crack length and the two different types of energy, I plot in blue how much stress the material is withstanding. I plot in red how much energy it's accumulating just by having open surface, the crack. Notice that there's a sweet spot below which the material has more crack energy than elastic energy. So it says, you know what? I'm going to live with this surface crack and not make it grow anymore, because that would cost me more energy. I can handle having some stress inside. Above that certain length, the material acquires so much stress energy just by hanging on to all that stress, whereas opening up free surfaces will cost it less energy. So it says, you know what, I'm just going to fracture, relieve myself of that load you're putting on me, and just create two free surfaces. Yeah, they cost energy, but much less than all that stress I have to endure with you pulling on. Whereas when the crack is small, it says, well, you're not putting so much stress energy, so I can live with these two free surfaces that I don't like anyways. So there's a trade-off between these two scenarios, and that length became known as the Griffiths length. And so Griffiths worked it all out, and he found that there was a critical stress that depended only on the material properties. E is the elastic constant, gamma is the surface energy. These are properties of the material, that's all we need to know. Length is just how long this crack is. And he said, anytime a stress at the crack tip exceeds this number, that part will fail. So if you're ever waiting at an airport, before your flight, you'll often see your pilot has to do a walk around. They always walk around the plane. One of the things they're going to do is take a flashlight and shine it on the turbines of the engine. They'll look up at the wings. That's kind of like a first order pass. What they're looking for is any telltale signs of fracture or scratches, especially surface scratches, that would indicate they've been pre-trained by the engineers. all you gotta see is look for certain signs and then just blow the whistle. And they've done it, there's a redundancy there. So the whistle will be blown way, way, way in advance to when a crack actually is growing catastrophic. But they're looking for telltale signs of fatigue, cracks, surface scratches that may be problematic to the flight to call the plane in, or say at least at the next service, at the next landing, take care of this. That's what they're doing there. And they're really applying in their head, heuristically, what the engineers have translated into a set of codes, the Griffiths criteria, among other things. So it turns out, again, the interesting thing here is these aircraft were not supposed to crash, but they had cracks that exceeded these lengths based on the material they were built. And what would cause the stress to go higher than this? The fact that the portholes, the windows were square. And so from that point on, they also started designing windows to be oval, blunter tips, which would then reduce the stress around the window so that it would always stay lower than this so-called Griffiths stress. So having fun? One more story? All right, last story, the Titanic. Right?
Don't we have one more?
Only one, I'm going all right, but, so the Titanic, this is a picture taken in the 90s. I think it was by the Cameron team when they were filming the Titanic movie. And what you see here is the Titanic cracked in two. That's not from what actually caused it to break. That was when the ship actually, you remember in the movie, when the ship went down just before it cracked, before our two protagonists landed in the ocean. And their love story ended while, they were sitting on the bridge up here. But what happened here? So 1912, so this is now over a century ago. The Titanic hit an iceberg around 1140. It sank 2.5 hours later. Most investigators up until the mid-90s, when NIST, the National Institute of Standards and Technology, for some reason, championed the case of getting material from the ocean floor and analyzing it and coming up with a revised version of what caused the Titanic to sink. I was a postdoc at the time in Urbana-Champaign, and I was considering employment at this, and I thought, well, that's pretty cool that they're actually interested in figuring out how the Titanic sunk. You figure they can do something better with taxpayer money, but that's fun too. So they concluded that the iceberg tore a gash through the hull of the ship, across the hull of the ship. And that was the leading story into the 90s. In 96, the expedition I just showed you revealed not a gash, but 6 narrow slits where the bow plates appear to have parted. So again, like the Challenger, you don't build the ship with one monolithic plate, you build it with plates that are riveted together. And what they found in the 90s when they looked on close and personal on the plates were rips in the lines, the rivets that bolted the plates together. So that in itself was interesting because it contradicted the theory most people had thought. They thought it just punctured a hole through and it was supposed to be unsinkable. And we all know that the unsinkable-ish thing didn't work because the plates that were supposed to, inside plates that were supposed to stop the water from going into the fall, etc. And so what people then started to suspect is that the rivets that had kept the plates together that made the hull of the ship popped apart. So it was literally unzipping itself because the rivets snapped. But why? Again, it has to do with fracture. This time it's more subtle, but still more related to what happened on the Challenger. So some metals become very brittle at low temperatures. There's something called the brittle to ductile transition. So most metals, like pig steel or the steels we use in buildings, they can withstand a large temperature range and stay quite ductile. In other words, they can take a certain load and then bend. Here you do want it to bend plastic. And unlike an aircraft wing, where when it passes a certain load, you don't want it to bend permanently because then the aerodynamics gets ruined. In this case, you have steel where you take a certain load, and if you surpass that load, it's okay if it bends a little bit, even irreparably, because it's still holding together overall. Bending a millimeter out of place, probably every component in your car, after some time of driving in Quebec roads, will never be aligned perfectly. It's probably permanently bent a little bit. But the car is in structural integrity. Hold the car works. And so you want the metal to stay ductile over a range of temperatures. Other materials have very low ductility, so they're brittle. Others still start their life at high temperatures being very ductile, very malleable upon loading, but do this dirty trick when they get cold and become brittle. Loss of ductility means brittleness. Think chalk. Up here, think silly putty, very gooey. And so it turns out that the rivets used to fasten the plates on the Titanic, because there was, again, a rush for production, were supposed to be made of something called pig iron. Instead, they were made of something called wrought iron. Moreover, they were wrought cast by hand in a rush. So it wasn't mass produced, they were very heterogeneous. It was discovered later when they actually took samples, analyzed them, went back through the books and realized, oh, these things were not built to spec. I guess no one at the time thought, a rivet's a rivet, right? No one ever anticipated this would happen. As a matter of fact, based on what we know from the steel that was used in these rivets, they were exactly following the blue curve. The Titanic was sailing in the North Atlantic, so it got cold. So when the iceberg hit it, the rivets were not operating at these temperatures, but they were operating cold. So they suffered a brittle fracture. So imagine replacing the rivets in your car by chalk. Then you hit a pothole, the car falls apart. Right? Kind of something like that. So it turns out if the Titanic was sailing in the Mediterranean, chances are these rivets would have held, the bow of the ship would have bulged in, but the ship would have just sort of deflected. And looked, rather unseemly, but probably at least they would have had enough time to evacuate. But because it was sailing in the North Atlantic, the rupture was immediate and rapid, and they didn't have enough time to survive, or most of them didn't anyways. That and the stupidity meant a lot of people had to die. So that's it. That is the end of this tale. Next week, next month, or next cycle, yeah, we'll go from disasters to supermassive black holes. All right. So I'm done, folks. Thanks for your attention. I hope you enjoy it.
Thanks so much for the talk. We have time for a lot of time for questions. So, if any questions, I'm very happy to answer.
Nikolas.
Dr. Provatas,
Yeah.
do you think as humans build bigger and bigger machines with more and more parts, it will become like almost inevitable that one part has this really strange property and someone's going to forget about it, and it leads to just the disaster we can't even stop necessarily?
Well, I can't speak to all devices, but aircraft have in the millions of parts. And, although I like the drama of an plane disasters, the show Mayday, I've seen every episode. I don't watch it anymore. You know why? Because it's boring. Because I've seen them all. There's that few. If you think of how many planes are flying and how absolutely safe flying is, the drama is just for pictures. The actual thing itself is so safe. So I think if the engineers do their job properly, then the answer to your question, at least in aerospace, is no. You can always design things so that if you're functioning every component within spec and people are diligent and, ethically behave themselves when they design, then there shouldn't be a problem. I think, yeah, if you're trying to cut corners, speed things up, make money, like the Boeing has just shown us, for example, a complete counter example of that. If your only motivation is just to make money and risk public safety, then, it turns out like beyond the 737, they found a slew of problems all based on negligence and just cutting corners. So I think it comes down to how we're certainly intelligent enough for the answer to be no, but I think we're greedy enough for the answer to be yes. Question.
Fault in using heterogeneous materials, model at micro level or macro level. Like, for example, I know that you're not supposed to weld like two different materials together if they're too different. But it's at the micro level, we still have something.
That's an excellent question, and it's true. You know, so you're not, even the same material, if you weld it on itself, the welding creates structure internally that's different from the base material that was originally fabricated. So, you know, we work with part of my group with Hydro-Quebec. They have these huge hydroelectric dams that just, at the core of them is big steel turbine blades that just turn and convert falling water to electricity. It costs them millions of dollars of revenue loss every time one of these turbine blades fractures. And what fractures is always at the weld joint where the turbine blades are connected to the shaft because of exactly what you said. There's a heterogeneity between the weld of the same material and the same material in its as-cast condition, because the conditions under which they were formed were slightly different, leading, remember, process structure. The processing was slightly different to create a heterogeneity, so you don't even need a different material. Even the same material processed differently on the same part could lead to fracture and failure.
What other disasters would you include if you had?
Oh, another aerospace that I love that is the Hawaiian is the Aloha Airways is like that one is an interesting one in fracture because there was lots of fractures on the airframe, smaller and larger ones, and a panel blew out. The planes are usually designed so when they fracture, it's not all one monolithic panel. There's, if you see, next time you're standing at the tarmac, you see that there's almost like patches on the body of the plane. That's intentional. So one blew out because it had a fracture that blew out at that point. And a stewardess, the only person to have died in that accident, was sucked out of the plane at that point. But as she escaped, her shoulders hit the ribbing that goes along the aircraft. And that created such a large pressure pulse that it exceeded the crack length of another crack that was lying along the fuselage, and an entire section of the fuselage just lifted up. So the plane ended up looking like a convertible. They were lucky because they were flying between two Hawaiian islands, so they had not gone higher than about 15, 17,000 feet. So the pilot was actually able to land it based on the integrity of the ribbing that still stayed intact. And so that's kind of both dramatic and a little comical. And it's a sort of, showcase of fracture mechanics. Another interesting one that's less dramatic and much sadder is we had an airplane crash in Canada off of Newfoundland in 1996. A Swiss Air plane killed 276 people. It crashed into the ocean with engines at full thrust, nose first, because the cockpit had caught on fire and there was no control. So the thing just became an arrow into the ocean. So it was dramatic. At least death was instantaneous. The reason for that, we switched gears, was about thermal conductivity of the wiring. They had installed a gaming system in first class that caused a lot more usage, a lot more current to flow, a lot more heating of the wires, but they had not replaced the insulation of the wires, so they burned and started a fire. Again, it was a materials issue. And in both cases, it's the kind of thing, had they taken the time to think about all the components that go into installing new electronics, they would have been able to easily prevent it, but it wasn't done. So there's tons of, so those are two sort of extremes. One is a little comical. One is, I remember again where I was when that plane crashed, and it was just devastating to just imagine that the people were watching themselves go to their death, because the pilot tried to land it, but he just burned up before he can dump his fuel and land in return to Boston. So it was really scary. And I was able to fly the next day. Go ahead.
That makes people showing that
That one was debris on the runway. As it took off, it clipped some metal that had been left there from a previous flight, and it got sucked into the engine, and much like the Challenger, it just caused an explosive decompression of the engine and a fireball. So there's a famous movie on YouTube where you can see the thing taking off, but it's not getting any lift because its engine has now started catching on fire, and it just sort of does this and right into the fields next door. So that too was pretty tragic. But that was just, again, I think just a bad accident. People didn't see that there was debris on the runway from the previous flight.
That's not a reason to just cancel completely the.
Well, I think that in that it was a bit of a gas guzzler and certainly was not making money. Because pretty much it was like, what was it, 120 seats, all first class, $10,000 each. So I don't think it was economically viable.
Show is always claimed. I think it was political.
Yeah. There's apparently a company, I can't remember the name anymore, trying to resurrect the whole notion of supersonic flight, but the Concorde, my understanding was it was, I don't know, I can't see how much money they were going to generate with that kind of expense.
Large is expensive.
Absolutely,
So.
absolutely.
it's just unfair.
Yeah, that's why lightweighting of alloys, you know, when you write a grant for lightweighting of alloys, the first sentence is always transportation. And aerospace is the number one, because just a small percentage of weight loss means you're saving a lot of fuel. Yeah.
Could you make some comments about the Hindenburg?
I'm afraid not. I'm not expert enough in that. I have not studied that, so I wouldn't be making anything intelligent. Sorry.
Okay.
How is like modeling and simulation changing things in your field versus experiment? And I'm also curious about like meta materials or like new types of materials that you find exciting.
Yeah, so that's a great question. Obviously, we are computational material scientists in my group, and the belief is that we are trying to understand the properties of the microstructure from the fundamental physics perspective. And we will often work with experimentalists who have labs who make, so right now the big thing for us, most of my group is working on something that I would say is most intimately related to additive manufacturing or 3D printing. Most aerospace components now, or many of them, are 3D printed, like entire engine parts, because it comprises, well, yeah. So it comprises basically extreme amounts of rare metals that are costly, so you don't want waste. As casting structure in place is not doable. So for example, you cannot, to form a rocket engine, for example, with all the cooling vents, in the old way, you'd have to cast each part, connect it. It would take months and months, probably years to do. Now, in a week, there's a company that makes engine parts that can do it in days. And so when we were working with GE, they were casting 747 engines with 3D printing, and their big problem there is very high strength, but they have lots of pores and defects that grow in them, and how to diagnose them based on these new, very rapid laser manufacturing techniques. So what they asked for us is to look at things like, what is the relationship between the particles, so-called precipitates, or voids, or cracks that grow in metal when you solidify them, even at the fundamental scale. And then the hope is that eventually we'll be able to simulate large enough components that would become relevant to something they can manufacture in the lab. So right now we're working mostly with 3D printing, and all the applications are aerospace, and all the applications about controllability of the component. In terms of metamaterials, the Airbus A350 and the Dreamliner, I would say over half is made of fiber reinforced composite, not metal anymore. And so there's an example of super lightweighting, much more flexibility. If you've ever flown on a 787, you see when it's taking off, the wing almost, it scares you a bit how flexed it is. That can't be done with metal. It can be done though with fiber reinforced composite. So I think as we become more clever at manufacturing these things, making them reproducible, making them, fit to spec, again, modeling will play a role. We don't deal with the metamaterials. We're still strictly on alloys because that's still the core component. 3D additive manufacturing is kind of all the rave now in materials research, at least in rapid solidification. So yeah. Yeah, I mean, you want to try to make sure that they're not a budget airline, because, there's a certain criteria of safety, and if you're a budget airline, you're probably as close to it as you can. So, but, in the end, I think by and large, it's there's so much redundancy built in that it's pretty safe. It probably won't be the reason why anyone will die. So Aristotle Onassis was transporting oil from Iran, Persian Gulf to UK and the United States. And at the time, the Americans decommissioned these battleships called Liberty ships. And Aristotle bought a couple. And they sank. And when he realized that these things are easy to sink, full of oil, collects insurance money. He started buying more of it. And like all smart, shrewd billionaires, didn't do it forever.
You'll need to add contact information for Mark Group before I can do that.
He just needed to do it enough to get rich and then bootstrap to the next investment. And then, of course, they killed him. They killed his son. There's a bunch of conspiracy theories about how Aristotle died, but yeah. But that my father was sailing on one of his ships in the 50s, actually. So I remember at that time the sailors knew that things are dangerous, but he didn't. I mean, it didn't happen every day, but it happened because he knew eventually, statistically, this thing has a faulty design. And now we know the Liberty ships. On my other public lecture, I had a Liberty ship, and it had the same thing, a kind of square door. And so it's very similar to the BOAC accident that cracked as well. So yeah.
Why NASA had so many disasters, but Mr. Elon Musk, he succeeded with everything without any failure.
Well, NASA's been around a lot longer than Elon Musk, so maybe after 40 years we can see what his track record is. Also, Elon Musk is 2020s. NASA, if you think about it, in all fairness, 80s, 70s. If the flight to the moon, the Apollo 11 was a testament to human ingenuity, right? They were working with the equivalent of what we would call a pocket calculator to do calculations. So considering the resources they had, I would say it was a fabulous achievement that NASA achieved, not just in the Apollo program, but also the space shuttle program. Disasters are inevitable. I'm sure Elon Musk and SpaceX and all this stuff will eventually, suffer some kind of accident. It's inevitable. So right now it's, I think, youth. Just it's still a young company. That's my guess.
Are you aware of any unique material science challenges in something like satellites or the ISS?
Not in that domain specifically. I mean, again, I think materials, lightweighting, that must be an issue for them even more than for aircraft, because putting things into orbit is super expensive, getting escape velocity. But I haven't really studied that topic, so I wouldn't be able to tell you. We're good? All right. Thanks, everyone. All right.
I think like how did the physics, research on the physics of materials then lead to
Regulations or
regulations, right? And how, for example, a factory in the USA, a lot of things are shipped from other countries, like Asia and so on. And how do we ensure that the regulations in one country match the regulations?
Yeah, and that's a good question. And this latest Boeing fiasco, further than the 737, the 737 is only a portion of it. But since then, for example, the part that makes the fuselage for Boeing used to be part of Boeing. Then they spun it off to Spirit Aerosystems, which is a separate company. So now they had this hearing in Congress over the summer and over the spring months. And it became very apparent that what was happening is that the quality at Spirit Airways was low. They were rushing to mass produce these things because their order sheet is ridiculously long. Right now, most airlines are even decommissioning old planes. That double-decker A380, which was supposed to not fly again, is back in commission because a lot of airlines can't meet the demand because Boeing can't produce it. And Boeing can't produce it because now they've been their quota has been fixed by Congress because they realized they were trying to overproduce and they couldn't inspect the quality of the fuselages they were getting from this company that used to be theirs that they spun off. So forget going Asia and abroad, even within the United States, the quality is hard to manage. And that's not because the engineers are not educated or not, it's just greed. It's just they wanted to meet their orders so fast, they were cutting corners. not inspecting as much. There was also, as part of the Congress hearing, it was again very clear that there was intimidation. If an engineer reported it to the managers, they were shut down. They were disincentivized to talk. And so again, to the question that was asked before, I think none of this needs to happen, but it has to be well controlled, and there has to be, you know, ethics involved. Okay. But to be sure, as we learn more stuff, then it becomes a regulation. So regulations keep changing as we learn more in every industry. Like the Griffiths criterion wasn't known, or it was published but wasn't known, but after it was known, it was now established protocol. And so as we become better, I think even with the carbon reinforced fibers, the join where they joined the aluminum was causing some corrosion. That too was, I think there were some people in the US, that professors actually, who did the research on that to look at corrosion. They immediately told Boeing, because they were funded, and they switched that up. So as we learn more, it immediately can get into service right away if there's an actual connectivity, you know.
And last message, if your name is Agan, I hope I'm pronouncing it correctly, yeah. You have won the Physics McGill bag, in sort of for, yeah, yeah, thanks everyone for joining. I hope you enjoyed it.